16 abstract. Okay, I'll just start because I don't have much time also. Yeah, so I will share my screen and yeah. Can you see my screen? Yes. Okay. So today I will be concluding the last part of this course, and I plan to to use already an inbuilt example to build a classifier like a model or something. So today I would be covering building machine learning pipeline in KNIME and also how to make your code or your workflow cleaner or something so as to particularly when you have too many nodes. There are several ways to encapsulate nodes into some meta node or component for readability and yeah, so that the whole screen doesn't just get messed up. And also, we can arrange our workflow properly. So without wasting much time, it might be a short section, but um as long as I cover what I plan to cover today. So we want to build a machine learning pipeline. It's very easy. Of course, some of us already have basic knowledge of simple machine learning pipelines already. But in KNIME, like I always say, it's very easy to work with nodes, and these nodes represent certain functionalities, and our job is just to drag these nodes and to configure them and use them. So this is a simple. So when you install KNIME, I think the last time we talked about it, there are some example workflows. And in these example workflows, you will see one, two, three, four, five folders, and you see basic examples, and in the examples, you will see four KNIME workflows: building a simple classifier, data blending, simple reporting example, visual analysis of sales data. And then you see also customer intelligence. Under there, we see churn prediction also. This is a machine learning framework where you can build a churn prediction model and also deploy the prediction model. And there is also another one called credit scoring. You can build a credit scoring model. There is another one called customer segmentation. You can just a basic customer segmentation use case. And then we move to retail. We also see some other, there are a lot of interesting things to look at. We might not always cover all, but they are also, just you can explore all of the folders and see. I think here these are the data for the example workflows that was used that were used. So here Yeah. So let's go to the basic examples already. The workflow has been built um, by virtue of just installing the um, KNIME. So now we want to build a simple model, a simple classification model. And the first thing we would always do is to read the file. And remember the last time I said it's always nice to make your workflow clean or things like that. And these are just ways you can, build your workflow. You can make it colorful or something. I mean, it's very easy. For example, these these boxes, they are things you can easily build. You can just right click, and I think you can click on new workflow annotation, and you see this box, something like this. So you can always stretch it anyhow you want. Um, yeah, so I mean, the goal is not to teach how to create this box, but just to show us why this example workflow looks, quite nice. And you can also click on the configuration, the edit um, icon here, and there you see the font size. Yeah, you can adjust to align center, or yeah, these are, I think this should be um yeah, these are the border colors, and these are the background colors. This is the, I think, the width of the border color. You can reduce them. Uh, yeah. And when you want to drag a node, for example, CSV reader, you would just drag it inside. And basically, this is what you see here. And you can go ahead to write on, um, yeah, you can write on it, something like this. And yeah, you can just make any comment or something you want, and yeah, you see it exactly like this. So I'm going to delete this because it's not the purpose of this section. So let's just build a simple classifier model. So first of all, it's an adult data set file, and basically when you read the data, it's just yeah we see we see a lot of information about people, their age, work class. I don't know what this is. It looks like some numbers or probably some ID. We have the education. We also have here the education number. Yeah, every education is numbered. Um, for example, bachelor's is 13, and yeah. And we also have occupation, we have marital status, relation, race, age, sex, capital gain. And we have also capital loss, hours, native country, and we have income. So um, the goal of this section, or yeah, this particular workflow is to build a simple classifier model, probably using any of the features, age, work class, up until native countries, to predict if their incomes would be less or equal to 50,000, or greater than 50,000. So yeah, and here we read data and we pass it on to the color manager. So the color manager is also another very interesting node that you can use to you know to annotate your data. For example, here, when is there a way? to color maybe income people, like you can, because here we have two classes here, income greater than 50 or income less than 50K. And if you want to know number of classes, of course, you can also use histogram also to check to check some the unique feature the unique values in this particular. Okay, less than 50, I think. Yes. Okay, I think it's a string, and then let's see. Okay, it's a string. We can also use maybe bar chart or so also to count. I don't think so. I think it basically works for numeric. I think it's also, yeah, we can group them. Yeah, but of course I don't want to waste much time. You can represent 50,000. You can rename the income with less than 50,000 with one, or you can use some unique labels to represent every unique value. Or it's two in this context. So, and here the column manager is you can choose whatever you want to group. For example, here the income for less than or equal to 50K, present it as red, and for greater than 50K as blue. You can also choose some other colors other types of colors you want. And when you run this, and when you open the data, you see here at the left, you see that this color has been applied to, for example, all of these are less than or equal to 50K. It's red, and yeah, greater than 50K, it's blue. So it doesn't really, I mean, just help for visualization, nothing more. But of course, this is just what the color manager is doing. And red for income less or equal to 50K, and blue for income greater than 50K. So now let's go to data partitioning. We know that if you want to build a model, you have to split the data into train and test split. And we create two separate partitions from original data set, training set 80% and test set 20%. So in the configuration, you can always choose the percentage of a training set you want. If, for example, you want 70% training, 30% test, you can just put 70, and KNIME would automatically use the remaining 30 for test. But let's stick to 80. Now, the next thing would be to sample. How do we want to sample? Do we want to use this, just pick from the top? At least it takes the first 80 examples from the top, and also linear sampling. So if you want to sample linearly over the whole table, and this also randomly, if you want to sample randomly, and this is stratified sampling. So basically, the difference between this is just it focus on, you can focus it on a column or on a feature, and then it splits it such that for example, if I'm splitting this 80% train set, even though the data is undersampled, it's still going to sample it. It's still going to sample it in a way that the training set will not be overpopulated with the particular label that is more prominent. So yeah, think about in this data, we don't know, we can be sure that our model doesn't is not biased, something like that. So, and I give an example. Imagine we have in our training set, let's say, if just as an example, if the greater than 50K is like 50,000, or let's say 20,000 examples. And we have the one, um, we have less or equal to 50K, let's say 5,000 examples. So let's just assume this is the number of our salary range. So what it means is that our data is not balanced. It's not balanced, and is imbalanced, something like that. So here in this case, we say that the less than 50K examples are underestimated. I mean, undersampled, something like that, or they are not. It's not balanced. So it's not balanced with the one of greater than 50K. So the possible one way to go about this is, how do we handle imbalanced data sets? So it's either we have to, now this by default, we assume that this is already undersampled, or because we have not started sampling at all, but let's just assume at this point it's still undersampled because we have now 5,000 examples, and we have 20,000 examples here. And one way to go about this is to reduce the number of greater than 50,000 to, let's say, 6,000 or so. And then we can now say that it's balanced. So now we have undersampled this, and then it's now balanced with, or more or less, you can make them the same or almost the same. Or what you can also do is to oversample this. That is, you use some techniques, some sampling techniques, probably based on we can generate data. If we can understand the underlying distribution of these undersampled examples, then we can now probably oversample it up to, let's say, we can generate 15,000 more examples, and then so that it can balance with this greater than 50K. Yes, another way to do this, if you don't want to go through undersampling or oversampling or something, or yeah, what you can do is, if you want to split this kind of data into 80% and train and 20% test. Now, if you do it randomly, it's possible that the 80% we would have more of this greater than 50 in this 80%, and we would have this less or equal to 50K. Not We just have a very little amount in this training set. And we don't want such, because the model will be exposed more to this greater than 50, because of course, obviously, we have more examples here, and more of these examples will be included in this 80%, and very few of these examples would be included here. And the model will be biased towards predicting this better than this. So one way to do it is to do the stratified sampling. So stratified sampling basically would just what stratified sampling would do is, now we have 5,000 examples, we have 20,000 examples. Now, if we are going to sample 80% for training set, this algorithm will ensure that we would sample almost equally in a balanced fashion. So just for context, since already we know that we have 5,000 to 20,000, this is almost ratio. This is 4:1 ratio, for 1:4. And instead of having more of this inside this 80%, the algorithm would sample in a stratified manner using the original distribution of um, of the examples. So in this case, the 80% will contain 40% of this, I mean, approximately, and also 40% of greater than 50K. So what we would expect to have in the data would be already we have, let's say this is 25,000. Yeah, 25,000. And of course, then we know that if you calculate 80% of 25,000, yeah, you can do the math. And then what is left? So when we say 80% of okay, I guess this is not the approach. So the approach would be first, we take the 80% of 25,000. And this should give us around 250 times 80. That should be, if I would use my calculator, that should be around 250 times 80 should be 20,000. Yeah. So what it means is that we need 20,000 training examples. Now, out of these 20,000, the question is, how do we populate these 20,000 training examples? Already, we know that the distribution of the class of the two classes here, they are completely imbalanced. So we have 1:4, 1:4. So how do we ensure that this 4 doesn't dominate this 1 in these 20,000 examples? And since we are using stratified sampling, now stratified sampling would ensure that out of these 20,000 training examples, 50% will go to this first class, and the other 50% will go to this other class. Then you see what we would have is something quite balanced, but yeah, of course, 20,000 is already too much because yeah. So how do we calculate 50% of this less than or equal to 50K, and also 50% less than or equal to yeah, greater than 50K? So what we do is we calculate this 50% based on their original yeah, distribution or something like that. So it will be 50% of 20,000, 50% of 5,000, then whatever is left, we are going to deduct it to get our training and test set. But before that, yeah, let's just do a very simple example of what I mean. So we need 20,000 training examples, but then we have 20,000 greater than 50, and we have 5,000 less than 50. We cannot make them 10,000 because even the less than 50 is not up to 10,000. So what we would do is to first of all find 50% of 20,000. Then yeah, that would give us we would have something like 10,000. Yeah, we don't have to do any calculation on that. 10,000 to 5. Yeah, that would still be more. Okay, and then yeah. Okay, yeah. So give me some. Yes. So 50,000 of 50% of 5,000 is 25. 50% of 20,000 is 10,000. Yeah. So Oh, that cannot be. How do we go about this? Okay, yeah. So we have to sample it such that um, what we need. Okay, we have 25. Yeah. So obviously, okay, yeah. So we will use this ratio, 1:4. So it will be 1/4 of whatever is here is 5,000. Then 1:4 of um yeah. Okay. I think I've written too many things. But I think in the end, what we would expect to have should be I think around 18,000 for this class and maybe 2,000 of this class. Yeah. So yeah, so that is how the ratio is calculated. So first, excuse me. So first we calculate the 80% on the 80% on the overall examples, which is 20,000. And then in this 20,000, we have to split it such that we would have a balanced sampling of 80% of 20,000, no, 50% of these and 50% of these inside of these 80%. So when we say 50% of 80%, yeah, something like this, and 50% of 80%, 80% of this would go to this, and 50% of 80% of this would go to this class. Yeah, so if you can also take your time to do the calculation, and yeah. So basically, that is what this stratified sampling is doing. And then when you choose income, it's going to act based on this data class. At the end of the day, we would find something like 20,000, 18,000 of these and 2,000 of these. And that is how you get the overall training set. Yeah, so we can run the code. Then we get, we have the first partition. This is the training set. And the next one would be oh, my system is freezing. Yeah. And the next one would be the test set. So this is the test set. And you can see it has sampled it in a way that we would have the less than 50 and greater than 50 to be balanced. Yep. And now let's move to the training section. We can build a decision tree learner. Here in our node repository, we have the nodes. You can use random forests. You can use decision trees. You can use any kind of model that you want. Or if you just click on models, you would see a lot of models. These are decision tree assembles. These are assemble learning, and you would have a lot of them. And yeah, in the random forest, we have the decision tree. Yeah, okay, I think it's under the analytics. Yeah, we can find this. Okay, this is decision tree, and this is decision tree assemble. So here we have random forest and gradient boosting. In decision tree, we have decision tree learner. We also have the simple regression. We also have this PMML simple regression tree predictor. And we have a couple of them. You can just have a look. Then if we now to configure it, it's nothing much of a problem because we need to put the class of columns we want to. So this is what we want. This is the feature we want to predict, the income and the quality index. And also, if you think about the partition, everything you include, every columns that are included here would be used for the training, except from what you specify as the income. I mean, unless what you specify um, as the output, so which is the income here. In our model, we have chosen income. So the income would be the class column that we want to predict, and every other columns would be um, the features. Yeah. So this is the output. Always put the label. This is what we want to predict, and the remaining columns we just put the predictors. And this is the dependent variable, which is the income, and the other columns are independent variable. So this income depends on the predictors we want to use. So when you run this, also we have it trains and we get some output. Yeah, so this is the decision tree output. Yeah, it's a lot of information. You can also, I think, yeah, this is here we can see some of the information on the decision tree. Yes, and then the next thing would be to now in the trainings in the partition we only use the you can see that we have two arrows for the partition. This first one is the first partition, which is 26,048. This is the training set, and we have this as the remaining 20%, which is the test set. And this is the model we train. And after training the model, we need a predictor. So we need a predictor, more or less like we want to use this train model to test, to see the performance on the test set. So there is another node called decision tree predictor. You can see it here. Decision tree, this is what we use to train the model, and this is what we use to test the model. So in the decision tree, there are two import ports. The first one is you have to move the model you have to ensure that you pass the learner into this blue port. And then the partition, the test data must go into the predictor. And then we just do this. So we are not training anymore. We are just testing. So we are using this train model in this predictor here. But please always ensure that you use the appropriate port, because the first one should always go to the learner and the second one should always go to the predictor. So when we click on this predictor, then you see when we can also open the table, then we see here some information on the predictor. This is the assigned probability. And here we have the predicted label itself. So Yeah. So this is the original income we have from the data, and here is what we see after training the model. So here is the probability that the income is less than or equal to 50, and this is the probability that the income is greater than 50. As you can see, it assigns more probability to this less than or equal to 50K. That is why our predicted outcome is less than or equal to 50K. So it has, the probability with the higher out of these two, it selects the one with the highest. But of course, there are cases where it is 50-50, and yeah, in such case, then it's just a kind of random guess. And for example, this is 92%, then this is almost sure that it's less or equal to 50. Here is a bit too, here is also kind of high, but it fails to classify this correctly. So this is greater than 50, but it predicts less than 50, even though it assigns 79% probability. And here we have the probability of 1 that the income is less or equal to 50,000, and here 0. But in the end, it's still wrong because we have the original label to be greater than 50, and it predicts less or equal to 50, even with probability 1. So how do we score our model? So we want to know the performance of our model. There is a node called scorer. If you're looking for a node, just always search for it here. There are two types of scorers. This is for numeric, and this is for entropy. So I think this is scorer used. There are other type of scorers that you can use. You can read about this. I think this uses, yeah, you can read about this. The node computes certain statistics between, yeah, you can read about it anyway. Yeah, I think this other one is for, yeah, it's a clustering. It's a scorer for clustering results. So every scorer has its own use. So now in the configuration of the scorer, we have the first column to be the original label. Then we have the second column to be the predicted label. That is the ones that the model predicts. And then when you run this, when you run the node, we get a confusion matrix. And this confusion matrix would give us how well our model is able to, the number of correct classification and misclassification. So here we have 4,527 correctly classified. That is for less than or equal to 50. We have 958 correctly classified for greater than 50. But we have 413 that was wrongly classified. So the model predicts greater than 50 instead of less or equal to 50. And here the model predicts less or equal to 50 instead of greater than 50, 615 times. So probably you can also think about, can I improve on this model? And if you look at this core, the accuracy statistics also, we have the true positive, that's this, the false positive, true negative, and false negative. We have the recall. Recall is quite good, but for this class, but the other one is not too good. Yeah, the F measure in general was fair, but not really the best that we want. So we have sensitivity and specificity, and yeah, if you go deeper into these numerics, so they give us, for example, in the confusion matrix, it calculates the recall. We want to know out of all the true positives, which one is correct compared to the original label itself. And here is 91%. Of course, this is obvious because the less than or equal to 50K is more. And also, due to the problem of imbalanced data set, we might not really know, but I think with the F measure, it also tell us better. Yeah, so we have other metrics that we can also look up for, and the formula for recall, I will show you. Yes, so when you yeah, so precision can be seen as a measure of quality and recall as a measure of quantity. So the idea of I think I need a better formula. Yeah. Yes. So here we have our okay, now it's asking me to log. Okay, so let's see this. Now we have the predicted values here. I mean, it doesn't matter the order. So you can decide to keep yours, the predicted value up or the actual values down. It doesn't matter. What matters is the interpretation. So now these are the predicted values and these are the actual values. So here we have the true positive. True positive means that the model predicts correctly the actual values. So here, and the true negative also. I mean, negative here doesn't necessarily mean negative in terms of interpretation, but just depends on your case study. Greater than 50 could be positive to you. Less or equal to 50 could be negative. To someone else, could be the reverse. So it doesn't matter as long as we only just use this for binary classifications. And since it's more than one, then we want to assume that one is positive, the other one is negative. And here in this place, what this false positive means is that the actual label is actually the actual label is negative, but the model predicts positive, which you see in red. This is called the type 1 error. The predicted value is positive, but it is false. So the model predicts positive, but it is actually false. It is not supposed to be positive. So it's a false positive. Here, it's just like false positive. The model predicts negative, but it's a false negative. It is supposed to be positive. So it's a false negative. It is called the type 2 error. And if I would click on yeah, so basically there are formulas that you can use to calculate these metrics. And the precision here is we take the true positives and then we will sum the true positive plus the false positive. So it is the ratio of true positive compared to to all the predictions. So here, this is the addition of these two gives us all the complete positive predictions from the model. And then if we take the ratio, it's just the ratio of saying, okay, out of all the positives that the model predicts, which one is actually positive? So the reference here is on the model itself. And so out of the true positives, what is out of all the positives that were predicted by the model, what is the actual fraction of true positives compared? And then in recall, the difference is it's just a flip. So here the reference is on the model because we are summing across the row here. But in the recall, we sum across the column. So we are summing in the actual sense out of what is the fraction of the true positive from the model compared to the actual positive itself from the actual labels. So this is where the recall comes in. And then the recall is also called sensitivity, and recall measures the proportion of true positives prediction among all actual positive instances. So this positive instance here is the actual positive instance in the data. And yeah, the recall is just telling us, okay, let us know which of the what was the fraction of the true positives with respect to this reference. For precision, it's just we are not using the actual values as the reference. We are using these as the reference. So you should know when to use one and how to interpret. So the F1 score is just is the harmonic mean, and it tries to give a weighted average between both metrics. This is also very useful in when you are working with the imbalanced data set, and it helps to balance the trade-off between the two. And then you can see the formula. Once you calculate your recall and precision, you can calculate the F1 score by applying this formula. And then, yeah, basically the interpretation, what we see from the model here is exactly what we are doing. This is the precision. So here we have the true positive and we have the false positive. So it's going to take this value divided by this plus this. So this here is just a fraction of a true positive and false positive. For sensitivity, as you can see here, this is sensitivity. It is just a recall. And I think it's always the same, yeah. Recall and sensitivity, I think, yeah. So recall is the same as sensitivity. That is why we have the same value. So here, what it's going to do, it's going to take the, from our formula here, it's going to take the true positive and divide it by true positive plus false negative. So true positive, then true positive to this divided by this plus this. And that is how we get this. Yep. So specificities for the true negatives, sensitivities for the true positives. And this is the F measure on the true positives, and this is the F measure on the true negatives. So from the formula here, we also see the recall. We calculate on the true, the F1 score, calculate on recall here and precision here. And then the F1 score for the true negative is also here. True negative, and false, false negatives. And here we have our true negative, and here we'll have our false positives. And then we can now calculate the F1 score for both classes. And this is exactly what you see here. The overall, the accuracy, I think it's the weighted average. I think it's the overall, as you can see, the accuracy is, I think it's the average of these two, or yeah, and then the coins kappa score also too. Yeah, it's a lot of metrics. You can also try to spend time to read about this. And this is just basically a simple pipeline to build a classification model. And when we go to things like churn predictions also, it's also more or less the case. And now I'm going to use this churn prediction to explain how to use components and meta nodes. And yeah, it's not that difficult. It's just the same process. Since we have these examples in our KNIME, we can also run through it, and you see that they combine two data sets. Probably they join the contract data and behavioral data. So yeah, I mean, it's just to understand the data. So here we have the Excel reader, the churn predicting model. It illustrates how to build and evaluate a churn prediction model. So when you read about the churn data set, it's just one of those few data that is used to. So churn equals 0 means that the customer remains with the contract, and churn equals 1 means that the customer will quit. I think it's just some kind of behavioral model to see if a customer, based on some factors, the customer would leave or the customer would stay. And in the first data here, we have the churn data, and the second part is I think this is the contract data also. Yeah. account length. Yeah, this is the international plan and some other things. Yeah. So when you join them, you join the contract. I think every customer or every employee. Okay. Here we join by the area code and also by the phone. So these two, it's a composite key. So we use them to join the data and we use just matching row. I think we talked about this the last time. Yeah. So and then when we join the table, we get this. Um, okay, I don't know why it's not closing. Okay, I think so many things are open. Let me close some. Okay, I don't know what is wrong, but it looks like, okay. Okay, cool. So yeah, and then we convert number to string, the area code. This is here. So we want to convert number to string. So there are times in KNIME, you can actually convert data types to another data type. So just use the number to string or string to number. The area code and the churn now would be converted to numbers. So I think formally here, the churn here you can see the churn is, yeah, I think it's already number. And where is the, okay, now we are converting it to string. Okay, now I see. So they convert the area code and the churn to, okay, I've not yet. So the area code and the churn will be converted from numbers into strings. We also apply the same color management for churn equals 0, blue, churn equals 1, red. When you click on the color management, you can configure it. Depends on what you want. But here it is churn, and you can choose any color you want. I can even decide to choose this green and red. When you open the data, we have now this green and red. So the partition 80-20, and I think it's nice to use stratified sampling. So even though the data is not balanced, at least the model will be exposed to the to both classes in the same proportion. But although it's not also, it doesn't really guarantee that the model won't still be biased, because if it is really, really, really imbalanced, then we would still nonetheless have more of the higher class. In the other explanation, I said 20,000 to 5,000. The difference also is very clear, because in the training set, we could have around 18,000, and in the other 5,000, we could have 2, 5 or so. It's still imbalanced. And one way to do is to undersample, but we can also try that later and see if the model would improve. That is in the formal examples. But it's still more or less the same procedure. We train we use the learner, we use the predictor. It is always like this, as you would always do in a standard machine learning pipeline. And here we can plot the ROC curve, and yeah, the area under the curve also. I think I would like to show the diagram. Okay, why is the diagram not displayed? I have to have it. Um, okay, let me confirm. Somehow, maybe I need to click on. Okay, let's create an image for the plot. Yeah, so this is the ROC curve, and yeah, as you can see, we see, yeah, we see the area. We see this line is a boundary line, and we always want our model to um, our ROC curve to always be around this region, somewhere very close to the peak for our true positive. So yeah, and this is just basically it. And yeah, for ROC, as you can see here, we have 0.891. Because now it focuses on the ROC just would focus on the true positive rate and the false positive rate. We don't want too many false positives. I mean, it depends on what we define as positives here. And we also don't want less false, for less true positives or more false positives. We want more true positives and less false positives. And then if we look at the axis, true positive moves along the vertical and false positive moves along the horizontal. So we always want to move in this direction to ensure that we peak at this point. At this point, it means we have 0 false positives and false positive rate, and we have 1 true um, probability, like a ratio of 1, which is probability that our model predicts perfectly the true positives. And yeah, if you also want to do it for negatives, or it depends on what we really define as our positives, but this basically is always the subject of interest. So when you are really focused on something as a subject of interest, then you can always use that as a positive label. Yeah. So let's see if probably this model can improve, because there are a lot of trainers. And if we look at the overall, the receiver's operating characteristics, the ROC, we see that we have a churn value of 0.891. So let's see, let's use a random forest, because random forest is also um, it's also a family of assembled architecture, and basically the idea is to, yeah, in a way, builds multiple decision tree learners, and it uses this kind of surrogate, combines all of these in the all of these learners, all of these decision tree learners, and tries to average. So let's see if we can. Let us try to just replace it. I mean, we don't have to. But first, we can, okay, I don't have to replace it. I can just use my training set in my, and then we can choose, we can configure our target column is the churn, and all of these would be our predictors. So when we run this, we would have, yes. So it's running. Let's now try for our, okay, there is a problem. Okay, due to missing information, okay. Let me see, pruning method. Yeah, I think, yeah, it is going to, let's see. Okay, if there are missing information, it's going to ignore. Yeah. So let's go ahead to, okay, I've tracked already the predictor. Output of bag of prediction. Random model. Yeah. So we'll connect this and then we can now use our test set. Like I said, the test set is always the second one here. So let's see. And let's try our scorer. I will just copy and paste. Let's see if there will be some improvement. In the scorer, if you look at the scorer here, yeah. So in the formal prediction, in the formal decision tree, we have 21 misclassified true positives and 26 misclassified true negatives. So let's see this. Wow, I think here it's we have 549 and 71. Here we have 566 and 57. So in as much as we have now more true positives in this random forest, our true negatives already reduced. So in this case, you see that formerly it was 71 here. Now it reduced to 57. And now we have more false negatives. So which is really not good for yeah, the model predicts negative, but it's actually false negative. So yeah, it depends. So the statistics would, so the question is what do you want as a trade-off between true positives and true negatives? So if you are more interested in positives, detecting positive more than negatives, then you have to focus on ensuring that your model, predicts more positive, such that a false negative will not be alarming. In medical domain, it's always the case that we don't want to misclassify a patient, or we don't want to classify a patient as negative when the patient is actually positive. So take, for example, cancer. We always want to ensure that a patient is correctly diagnosed with cancer. And if you say, okay, this patient is not doesn't have cancer, and then I mean, in that case, you have wrongly classified a patient as a negative when the patient is actually positive. So in that case, we want to always reduce false positives as much as possible, and increase true negatives. And it could also be different in emails, spam, I mean, to classify an email as a spam or not. So, yeah, things like that. So it depends on the domain, and what is positive to some might not be much of a problem, but what is negative also might not be much of a problem. To some other domain, it could be the reverse. And yeah, always be careful of the metrics, in particular when you're building a classifier model. So you can use some of these metrics that we talked about, the recall or sensitivity, specificity, and these things to see if your model is actually working well. Also, you can be more, you can create more strict rules or more strict borderlines to to how your model predicts. So, for example, let's try the ROC curve, and what let's see the output for our this random forest model. Okay. This is just giving us the confidence. Show the configuration. Okay. Okay. Here we have our class, and then we have the prediction. Normally, it should be like this also. Okay. Let's see. I don't know if it will work for the confidence, but doubt. Okay, it works. Yeah, we have almost the same. Now we have 0.89. The other one was, I think, 0.891 or something. Okay, then pretty much looks like the decision tree gives us a better overall ROC, but it's not too far from what we have in random forest. Now let me go to the last part of this section, and it's just how we can, make our code clean and cleaner. So yeah, now when you look at this kind of workflow, it's a lot, and well, this is not it's not a lot compared to how we would always have it when you are really building a very huge workflow. So what they would always want to advise is you can split your workflows into components and think about component as it's just it's just trying to arrange or gather things together. So, for example, is it possible to this? So I see from here to here, can we just reduce it, or can we find a way to encapsulate this pipeline so that it's going to shorten, the workflow? I can decide to select these four nodes, and I can create a component. And yeah, I can create a component and say, okay, this place is joiner up to partition. And with this, you don't need to, all of these, all the four nodes have been, combined into, everything has been encapsulated into this component. And when you run this component, it's like you are running the whole four node in between, and you can see. So when you double click, when you can right click, and you can also expand. So you can take it back if you want. You can also decide to take it. So let's leave it as it was. And yeah, you can also open it if you just want to see what is inside. So when you open it, it creates this, you see another interface. For example, this is just the component input and output. So what it means is that if you look at the original, um, okay, system is just not too, it's very slow today. Yeah. So we can, let me go back. I don't know what's wrong. Yeah. Oh, I can't even go back. Terrible. Okay. Okay. So here you can always open you can open it, and you can work with this workflows. Yeah, you can edit whatever you want to edit inside of this component. But in the main workflow, you would always have this just one component, So instead of having those four, now you've gathered everything into one. And you can also do the same for these, 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 these. I can decide to call this, you can create components. You can just say the training up to this call. So, or you can just put it as a model training to evaluation. And you see everything is just, yeah. Now this annotation would not be, oh, I think I made a mistake. I should also include them too in the, so when you are creating meta component or meta node, always ensure that all the, for example, these training labels that we put on the arrows, always ensure that they are also highlighted. So let's create component and let's see model, let's see decision tree, because now we have random forest and we have decision tree. Let's say decision tree model. Yeah, I think it should be enough because when we talk about model, we understand that it should be from training to evaluation. And I can decide to also call this okay, cool. I can decide to also call this random forest model. And now what you have just seen is, keeping your workflow clean and without too many things on the screen. I can even decide to say, okay, this should be, yeah, this should be read data or, yeah. I mean, it's just an example, you understand? So here I have my joiner, but I could decide to put the joiner into this read data. It doesn't matter. It also depends on how you want to structure work. So this is just an example. So when you open this, you see the joiner, blah, blah, blah. Probably we could have combined this joiner with the first component, and we can use this as, we can include the partition inside the model. And yeah, you can just clean it up. I mean, it doesn't have to be like this exactly. It's just an explanation. I can decide to join the partition with this model, but because partition is different from the decision tree or random forest, or I could decide to just leave it as its own meta node. You can, in fact, I can let me collapse this. I can expand it. You can decide to yeah. So when you do things like this, yeah. So I mean, it's not clean, but you can always arrange them properly. So here, as you can see, you can decide to leave it like this if you want. You can also decide to, yeah, it depends on how well you want to clean your data. I can decide to, um, yeah, I can decide to, I wanted to do something. So once you run this model, everything everything here and before it would run. And you can also decide to leave it like this. It doesn't matter. So this is basically how you create components. You can also use meta nodes. They are also meta nodes, but they are also advantage. Meta nodes at its own advantage. But I think component is very yeah, versatile because you can use components in different workflows compared to MetaNote. So you can decide to leave your joiner like this, and you can decide to add the partitions to the model, or you can just leave it like this. And you can just decide to combine these two. You can just name it maybe data processing or something. Yes, and you can have, so you can work with the nodes, components connected. And so the most important thing is when you want to see what is going on in a component, you have to expand it. And for example, this joiner is going into this data processing. So what you should note is that this component is expecting an input and is also an out, it's expecting an output. So when you expand it, you're going to, oh, I've expanded. Okay, let me take it back. I should open, not expand. If you click expand, you take it back to as it is. So when you open it, you see that this inside the component, we have these two nodes inside the component. And the component here, the input is just some nodes coming from the joiner. And here from the output of the component is just also the column manager moving to the partition. And this gives us an idea of what, for example, in this component, there are two inputs. There are two internal nodes coming, two internal ports. That is the partition from the training and from the test. So let's see what it would look like if we open it. So here you can see this one is the training and this one is the testing. So this one is just like a mirror, or would I say it's just like it's saying, okay, in this your component, there are two inputs. There are two ports coming into this component. And here, because there are no output ports, it's just locked. As you can see, it is locked. So locked, node locked. So there is no output. Here you see dedicated component input 0. Here you have dedicated component input 1. Here there are no inputs at all. And if you notice here, there are no output. And there are no output here because here in this component, the model, until the last node that I encapsulate in this component, there was no output. If there was an output port, you would have seen this output port. Here, you see that there is an output port here. And then when you open the component, you see that there is also, okay, pass on component output 0. Okay, yeah. So I guess, okay, yeah, this is the input and this is the output port. Okay. Let's go back here. I guess it was, yes, here. So there is no output, so there is no arrow coming into this port. Yeah, I think basically that's just it. So you can also play around with it and see what it looks like. Most times, it depends. If you're not using if you don't build too big workflows, you don't have to use component. You can just use it when it's required. I mean, if it's not a lot of nodes and your arrows, your ports, then you can just leave it as it is. If you feel like, okay, this is better and cleaner, but you have to ensure that you create your component in a way that you can understand it so that you don't just create component and you don't know how to access your component. For example, if I say, okay, I want to do some filtering, you can always go to data processing. And the interesting thing is that when you open your component, you can always add, let's say, a row filter. So when you add a row filter, you can always so you can always still work on, you can always edit the component just like as you would have it in the normal workflow. So for example, if I want to, let's say, filter a role, yeah, it is not, let me run it until that point. So that, okay, yeah. Yes, so if I want to filter a role, you can do anything. You can add your criterion. You can say, okay, I want to filter churn, that is, or let's say you want to filter state. First of all, let me see if I can choose one state. Let's say I want to filter just NY. For New York, I can now come back to my component and I can filter based on New York, NY. NY, state plus NY. And when you're done, you can decide to run it. You can decide to run you can decide to run, sorry. You can decide to run it here inside the component, or you can just decide to go back to to your node and run it. And then when you run it, yeah, you see that now we can run our partition. And you'll be surprised, not really surprising, every state would be filtered based on New York. And it is now NY because inside of this data processing, we added a row filter. And as you can see, normally I don't know why my tabs don't click. I think there's a problem somewhere. I don't know, I have to click and double click, yeah. Yeah, so so why do we need components? So we need components so that we don't have to do too many things in the main workflow, you see? And inside of these components, we have nodes. For example, if you want to work on data processing, just right click or you can open it. And then inside this environment, you can now continue to process your data. And when you're done, you can just save it and go back to your main workflow and you run it. Everything that you have done would work. But of course, you want to test if what you have added is okay or not. So if it's not okay, it will give an error. But let's just assume it's okay. We can run it directly from here. And as you can see, it's green. And now that it is green, if you go back to your main workflow, it's already green. So in essence, you are doing most of the node work. You are building the workflow inside this component, and this component the components are already, so every component should handle a particular task. So think about it as in a production plant where you have machines that are in charge of this, and these machines are in charge of that, and this machine. So this is like a machine. It's a data processing component. So this part of the workflow is responsible for processing data, anything data. Of course, I didn't include this in any component. So if there is a node that you feel like cannot be properly classified, or you don't want to, capture it, or you don't want to you don't want to put it into a component that would wrongly classify that node, then please don't put it in a component. Otherwise, you won't know where this node belongs to. You understand? So here, this is a decision tree model. It means from the decision tree learner until the score, I know it's here. I'm going to find it here. And if I open it, you can see it here. From the decision tree learner up to the scorer or the ROC curve, you would always find them there. And interestingly, you can run anything from anywhere. So here too, The same thing. Once you run this partition, here you can always run anything you want to run. So here you can run it. If you run it, you will still get your normal result. What it does, so at this point, all the influx, all the nodes, all the work, all the flows before this point would continue to pass the information down to the endpoint. So yeah, same 2 year, you can run it and you get your result. So if you want to view your result, then you can click on the node and you can view your result. So that's also the good thing about working with with components. You can also work with meta node. There's another one called meta node. But the interesting thing about, I mean, they serve the same purpose. I think if you look it up, you would see also the difference between meta node and component. Yeah, sorry, I don't know. Suddenly, I didn't know what happened. I was talking for some minutes and um, yeah, but I guess we are close to the end of the class, and yeah, I'm sorry. At the point I was just talking, I didn't know my Zoom had already, you know, gone off, and yeah. So I was talking about meta node. Meta node is just like it's just like component too, and you can also wrap your encapsulate your nodes and encapsulate your nodes to a non-meta node. And it's more or less the same. The only difference is that um, yeah, if you I was talking about the difference here, that these are just some of the um, so this is a summary table showing what a meta node can do and what a component can do. So both of them help to clean up messy workflows. And but Metanode doesn't have configuration settings, doesn't have a chart and plot view, doesn't isolate flow variables, but component can do all of this. So you can also read about component. But both of them can be very helpful. They serve almost the same purpose to clean up messy workflows. Yeah. So I think that's just it. And sorry for the break in transmission. I think I was here the last time. No, I think I was on this churn prediction. I talked about it that you can deploy. Um, I talked about that you can use your pre-trained model to you can deploy it and you can test it on your probably data. So when we were building this model, if you noticed, um, we saved our model as a PMM writer using this PMM writer node, and yeah. So when you want to deploy it, you just need to read we need the PMML reader. Just specify the path to the model and the name of the model with the extension PMML. And when we are done, this is the data we want to predict. So if you read it, it's just one example, probably one example we want to test. And when you test the data, you can just, you know, yeah, and you're done. You can you can build a report on this, and this is just the prediction. The model predicts one for the churn. Yeah. So I'm really sorry. I was talking for about 10 minutes. I didn't know I was completely off Zoom. I don't know, my Zoom just shut down unexpectedly, and I didn't see there was no sign it shut down. So, and since I was sharing my screen, I didn't even know I was out of Zoom. But that is basically it. Today we covered building simple classifier model. We also use random forest decision tree, but I mean, there are a lot of models. For example, there are linear regression model here. There is also, I think, a logistic regression model, as you can see. This is the learner, this is the prediction. So every model has a learner and predictor. Use the learner to train and use the predictor to predict. I think we also have MLP, multi-layer perceptron predictor. So it uses a simple neural network. Also, you can see if you read here the maximum number of addresses. No, it's not really simple. You can specify the number of hidden neurons or layers that you want, so which is also very effective. You have a random forest. You have a gradient boosting. Yeah, you have a lot of machine learning models you can use. You can train them. Yeah. So basically, that's just it. And I plan to end this section. Yeah, now because I didn't want to go more than what I should cover today. But I think that's basically that is just basically the whole idea of KNIME workflow, from data cleaning to pre-processing to statistics to visualization to building machine learning workflows. Yeah, these are some of the things we can use KNIME for. There are a lot of interesting things. I also haven't used KNIME in a while, and most times when I use it, I always learn new things. So you just need to continue to use it and look at it and play with it and explore it. As you continue to see new things, especially notes. You can't use all of them. So keep just playing around with the ones you can lay your hands on. And yeah, also look at these example workflows. The example workflows are very, 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 very important because they cover so much that I also didn't talk about. And from the basic examples, there are also visual analysis, as you can see here in this. There are visual analysis of sales data. You can look at it and see what's going on there. There's also customer intelligence. Yeah, we have done this. There's credit scoring. This one is also a machine learning model that checks the score of that helps to predict the score, the credit score for an individual based on some factors. So here they use the meta note, as you can see, they used meta note. And they also talked about meta notes here in this particular examples, in this particular example. So here you can expand it to see what is in the meta node. And when you open it, you can see it's a lot. This was also what I was talking about. You have the normalizer until the cross joiner or whatever. So, and then they continue. So here, this meta node trains and cross-validate a neural network. This trains and cross-validate a support vector machine, train and cross-validate a decision tree. So we have three models here. In each of these meta nodes is handling different models. And here they concat. So let me run it to see what it looks like. But they concat, so you can choose your own algorithm and concat it with the other algorithm. Check if your algorithm performs better. So when you use three models, you always want to know which one performs better. So I think probably concatenating the result by something like this. As you can see, this is for the neural network, this is for the support vector machine, and this is the decision tree. And then you pick a sorter, and you can just build a batch or something. I think I have to generate an image. I think what they did here was they tried to compare. You can sort by accuracy or something. Yeah, so here is a support vector machine. It has an accuracy of, I think, 74. Here is the neural network slightly lower, and here is the decision tree is the lowest. So here it's safe to say that the support vector machine has the best accuracy. So you can use that. So you can always look at this workflow. So you can use a template, and you can use the template on your own data, and you can play around with it. So, but when you're using template, always be sure to understand what the template is doing. For example, in every of these meta node, they did a lot of things there that you can also look at. And it's nice to see that everything is well described, labeled, and as you can see, the accuracy, a table is created. So read it and understand what it is doing. And then you learn more by doing, not just by listening to people talking, and yeah, so you learn more by doing. So I wish you guys all the very best, and yeah, hope to see everyone sometime again in the future. All right, I will be ending this section, and if there are questions or anything, you can also ask before I end this section. Thanks a lot, and sorry again for the break. Yeah, it was not intentional. Thanks. If there are questions, you can ask. Otherwise, then we end the section. But we'll send it. We are going to. I'm going to send. We are going to send the video to YouTube. Okay. I noticed Adelucy, Rachel, and Adiola Obadoye. Are there any questions from your side? All right. In the absence of none, then thanks a lot. Bye.
Thank you, sir.
Yeah.